Good morning, students. Welcome to the lecture 2 of engineering workshop on pattern materials and types of patterns. So before we understand pattern materials and types of patterns, let us have a recap of the previous lecture where we tried to discuss briefly about the casting, what casting is all about, and how does this casting takes place. So in the last class, we have seen the overall view of what casting process is, where we have understood that there is something called as a mold preparation for casting to be performed. And this is a mold that I was talking about in the last class, where the mold preparation is made basically by using a flask, which is a combination of cope and drag box. Yeah, you can see here the bottom one is a drag box and the top one is a cope box. And we have seen the different functions of the pouring basin, where I have told you that the pouring basin is basically used to reduce the turbulence flow of the molten metal. So generally, and I'll just give you an overview of the entire casting in just 2-3 minutes. So what we have discussed is, in order to produce a component, we have to prepare a mold. And in that mold, there is a cavity. And in that cavity, you will pour the molten metal. And once the molten metal gets solidified, you will get the final product. So now you can understand, in order to prepare the mold preparations, we require the following things like cope box, drag box, core, chaplets, pattern, riser, runner, gating system, and all these things, which we have discussed in the last class. Now, what you're supposed to do is, if at all you want to make a product from aluminum material, then what you're supposed to do is you take aluminum material and place it in a furnace so that the material gets melted into a liquid state. And when during the time required for the aluminum to get melted, during that time, what you can do is you can prepare the mold. So how the mold is prepared? You take a drag box and place a pattern in it, and then pour the sand and ram it hard, and take the and revert back the drag box and take a cope box, which you have seen in the last class video, where you revert it back and then you place a cope box on top of it, place another pattern, this cope pattern, and then pour the sand and ram it. And in the cope box, if you observe carefully, along with the pattern, you also have something called as a sprue, runner, riser. Okay, so these are the other things that you are supposed to place in the cope box, and then pour the sand and ram it hard. Now if you see, by the time you prepare your mold, the material in the furnace would have melted. So now shift the molten metal from the furnace to a ladle. So you can see something called as a ladle here. So in the ladle, you pour the mold, transfer the molten metal from the furnace to the mold. Wherever you are preparing the mold, to that place you can transfer the molten metal. So you pour the molten metal from the furnace. Inside the furnace, you have a crucible. Inside that crucible, you have your material is there. So you transfer the molten metal from the crucible inside the furnace to the ladle, and through the ladle, you take it, and then you pour this molten metal into the mold that you have prepared. So during this process, you pour the molten metal into the pouring basin first, so that the turbulence effect of the molten metal is reduced, and then the laminar flow of the molten metal enters into the sprue. So you pour the molten metal here in the pouring basin, and then it enters into the sprue, and through the sprue it travels through the runner and the ingot and finally reaches to the mold cavity. So the entire thing is called as a mold, and the hollow space inside the mold is what we call it as a mold cavity. So in this mold cavity, the molten metal fills. So if at all, as I have discussed in the last class, if at all you require a hollow component, then you place something called as a core. So when you place a core, which is a solid component with the support of the chaplets, and when you pour the molten metal, the molten metal will not fill the place where the core is at. So at the end of the solidification process, if you remove this core, then you get a hollow component. Okay, so this is what we have discussed. And also we have discussed in the last class that the riser is having two functions. Can anybody say what are those two functions of riser which we have discussed in the last class? Why riser is important? You can type your answers in the chat box. Yes, anybody? Okay, acts as a reservoir, whether the molten metal is filled or not, correct? Okay, fine. So okay, so there are two functions of riser. One is to make sure that the entire molten metal is filled or not. The other is to compensate the shrinkage. As I have discussed in the last class, the compensate the shrinkage means during solidification, the molten metal during its solidification, it contracts. And that contraction is being substituted with the additional flow of molten metal coming into the mold cavity from the riser. Now, I have a question. Why the molten metal is entering during contraction? Why the molten metal should enter from the riser but not from the your runner and ingate? I repeat my question. I am saying that when the molten metal is filled in the mold cavity during solidification, the molten metal during solidification contracts, and because of the contraction there is an empty space. So that space has to be filled again by the molten metal. Now I am saying that filling is being done by the riser. So the molten metal that is present in the riser will flow back into the mold cavity. The molten metal present in the riser will flow back into the mold cavity and it compensates the shrinkage. Now the question is, why only the molten metal should go from the riser but not from the ingate or the runner? Is that clear? Why the molten metal should fill from the riser but not from the ingate? Okay, because it is high, it is in higher height than other parts. Of course, if you see carefully, uh, sprue is also on the same height, right? So the molten metal can flow from the sprue to the rise runner through the ingate and then enter into the mold cavity. Ingate is closed. No, it is not closed. It is present. You, for time being, you forget about this riser. You just focus on the open riser. So you assume that there is a sprue, there is a runner, there is an ingate, and the molten metal can flow through this path. Why only from the open riser? Because the metal in runner also gets solidified. Okay, so somebody is saying that metal in the runner gets solidified, so it is not possible. But then why on then how come the metal in riser is not getting solidified? If you say that the metal in the runner, which is almost in the middle of the mold, is getting solidified, then how come the molten metal which is exposed to the environment is not getting solidified? Yes, somebody can answer. Think over it. We'll discuss the answer in the next class. Have a thought about it, that when you say that molten metal in the runner which is entering in through the in gate is getting solidified, which is almost in the middle of your mold, whereas the molten metal which is exposed to the environment, open atmosphere, is not getting solidified. See, somebody is saying a pressure temperature difference. Yes, the temperature difference is very high where molten metal which is exposed to the environment rather than the molten metal which is present in the mold. So think about that. We will discuss that in the next class. Now this is all about the last class summary. Now we'll proceed further in trying to understand. If at all you have to prepare this mold cavity, you require something called as a pattern, which we have already seen in the last class. That pattern is a replica of your end product. So how do we make pattern and all? Okay. So before we try to understand how to make the pattern and all, uh, tell me what is different pattern materials. What are the materials with which you prepare a pattern? So before you understand pattern preparation, like what are the different types of patterns that we use, first we need to know what is the material that is being used for making a pattern. Yes, anybody? Okay. Wood, wax, metal, clay. Sand is not the answer. Pattern is not made from sand. Wood, metal, clay, wax. Okay. So on what basis you are saying wood is best, plaster of Paris, wax, all these things? What is the basis? Wood, metal, clay, plaster of Paris. On what basis you are saying that these are better? Flexibility, fine. We can mold it into a perfect dimension, required resistance, easily shape. Very good. Very good. So, following other things, the pattern material should be, as you are saying, as exactly, it should be easily manufacturable, it should be light in weight, it should be strong and hard, durable, resistance to wear and abrasion, resistance to corrosion and to the chemical reactions, and dimensional stability and unaffected by variations in temperature and humidity. And finally, it should be a low cost material. So these are the requirements for selecting a pattern material. The pattern material, the material that you choose for preparing a pattern should have should be light in weight, it should be strong and durable, it should be easily machinable, because only if it is easily machinable you will be able to mold it into the required shapes very easily, because we understand that the process that casting is all about is to prepare complex shapes. So if you want to make a complex component, then the pattern should be easily manufactured into a complex shapes, and at the same time the component, the pattern that you are trying to prepare should have a dimensional stability. If it loses its dimension, then it is very difficult to get a same shape or size. So as you said, following are the materials that are used for preparing pattern: wood, metal, plastic, plaster of paris, wax. Now what are the factors assist in selection proper pattern material? So it again depends upon how many number of components that you are preparing. If at all you are producing a large number of components, let us say 1,000 or 10,000 components, then what kind of pattern material I have to choose? If I'm going to produce only one or two components, what kind of pattern material I have to use? So again, the selection of pattern material depends on these factors: the number of products that you want to produce, how much is the dimensional accuracy and the surface finish that you require, and the kind of molding, that whether you are going for a sand casting or a shell molding or investment casting, which casting process you are choosing. Okay. And finally, the shape, size, and complexity of the casting. All right. So these are the factors on which the pattern material depends on. Now, can anybody tell me what are the difficulties with selecting the wood as a pattern material? Because everybody, majority of you have said wood is a pattern material that is most widely used, which is very well correct. But can anybody think of what are the difficulties of selecting wood as a pattern material? What could be the reasons why, like, wood has certain limitations? What are the limitations of wood? Yes, somebody can tell me. See, wood is having, okay, let us come in this way. Okay, let us come in this way. First, let us try to understand what are the advantages of wood. Let us try to understand what advantages. What are the benefits of choosing wood as a pattern material? Yes, somebody said it swells. Correct. It's not flexible, less in price, burn into ashes in fire, impurities, lightweight. Okay. See, these are the advantages and the limitations of wood as a pattern material. The advantages are It's light in weight, inexpensive, easily available in large quantities. As I said, wood can be machined into whatever shape you require. You can get good surface finish if you do a finishing process of a wood. You get a very smooth surface finish, just like you have a wooden doors, which is very smooth. You can get a good surface finish from wood, and wood can be preserved for a long period of time. Okay, it has a very good advantages, but at the same time you have a disadvantages or a limitations. Let me tell you, it's a limitations. Now, what are the limitations of wood? Yeah, it is already there on the screen. You can still spell it out. The major problem with wood is swelling, dimensional inaccuracy. In one sense, you can say it's a dimensional inaccuracy. The reason is when you use wood for preparing a mold cavity or mold is composed of sand, clay, moisture, or the water content. Now, when once you place a wood and pour the sand and then try to ram the sand to get a mold, so the moisture content that is present in the mold is being absorbed by the wood pattern material. The wooden pattern tries to absorb the moisture content from the sand, and as the wood is absorbing the moisture content, in a due course of time, you will lose its dimensional accuracy. So thereby, the wooden pattern becomes dimensional unstable at a certain period of time. So the absorption of moisture by the wood leads to the dimensional inaccuracy, and sometimes even it gets shape change, in the sense like when it swells, you get a different shape. Okay, so that is a major limitation of wood. So that is the reason why when I was discussing about the factors in deciding the factors deciding the selection of a pattern material, one of the aspect is the number of components. So if the number of components are to be produced at 10,000, and if you are going to use a wooden pattern material, maybe after 100 components, the wood may lose its dimensional accuracy. So in such a case, for large mass productions, you have to go for the metal patterns. So here comes the metal patterns. So whenever the number of components that you produce is a large in quantity, let us say 10,000 components I have to produce, then in such cases, I go for a metal pattern. The reason is metal patterns are dimensional accuracy is high, dimensional stability is very high. Metals doesn't easily absorb the moisture and the swell. So the limitation that we have in wooden is been overcome by using a metal pattern. However, metal pattern have its own limitations. But before we look at it, we just try to see what are the different materials that are used for preparing a metal pattern. You can go for aluminum alloys, steel, cast iron, brass, white metal. These are the materials that can be used for preparing a metal pattern. Now, as I said, the advantages in metal patterns is that they don't absorb moisture, whereby dimensional stability is ensured. So the accuracy of dimensional tolerances, and it also have a good reasonable amount of longer life. And look at the limitations again. Limitation is it is expensive than compared to the wooden pattern. Okay, the material get rusted, that is corrosion takes place. As it is a metal, the moisture content doesn't change the like it absorb, and metal doesn't absorb the moisture and then swell it, but of course the moisture content on the surface of the material can leads to corrosion. So metal patterns generally, if it is a ferrous material, we all know that ferrous materials get rusted very easily. However, aluminum alloys doesn't get rusted that easily. Okay, but aluminum patterns have its own restrictions in terms of the pattern preparation. And metals cannot be machined so easily as compared to the wooden patterns, because uh, we all know that some complex shapes machining by for a metal is difficult. There are difficulties in machining complex shapes on metals patterns. Okay, so the major limitation in metal pattern is the machining and the cost, and the other thing is your corrosion pr- process. And the next is a plastic. Plastic is very much light compared to the wood, and it again depends upon which type of wood and all, and the type of plastic. So plastic is generally lightweight, durable. It gives a very good smooth surface finish. See, the reason again, the reason why we are stressing about the smooth surface is your end component surface finish depends upon the surface finish of your pattern. If the pattern is smooth, the final product will also have a smooth surface finish. If your pattern surface is rough, then obviously your end component surface will also be rough. So depending upon the surface finish of the component requirement, you should also consider the selection of a pattern material. And plastic, no change in its size and shape, that is dimensional stability is high, and there is no wear or corrosion issues. It is a very good wear and corrosion resistant property. You have a very good surface finish, as has been said. Okay, but what is the limitations? Okay, the limitations are the plastic patterns are fragile, and thus light sections may need metal reinforcements. Plastic patterns may not work well with when subjected to conditions of severe shock, as in machine mold. So you can prepare complex shapes in one sense, but at the same time, when you have a sensitive sections where the plastic material will not be able to withstand the shock that comes into the picture when you ram the sand to get a mold. So there are certain issues with this plastic. Of course, as we said, it can be used for small castings only. You cannot make a large size components of plastic or plaster of Paris, gypsum. Okay. And finally, wax. Wax is a pattern material which we use generally in investment casting process. So when we come to the discussion on investment casting process, we'll be discussing how wax patterns are prepared. Okay. So generally, wax patterns are prepared by using die molds, metal molds. Okay. So by the time we come to investment casting discussion, you'll be able to understand what I'm talking about. Okay. If you have any questions, you can just keep typing it. Okay, somebody is asking, should we use a metal with more melting point than the molten metal? Yeah, exactly. Not exactly. So, see, we are not preparing a metal mold right now. We are just looking into the sand casting. So, the metal pattern can be anything. It need not be a material which is having higher melting point than the casting material. The reason is the pattern is used only to make a mold cavity. Once the mold cavity is ready, you will take out the pattern and then pour the molten metal. So nowhere the molten metal is coming in contact with the pattern. Only when you remove the pattern, you will have a cavity. And in that cavity, the molten metal is been full poured. Okay. So it doesn't matter whether you have a wooden pattern or a metal pattern, molten metal will not come into the contact with this pattern material. Is there any material which does not have any limitation? No, every material has its own limitations. There is nothing like there is a perfect material. See, we have to make certain decisions based on our understanding and based on the requirements. If my requirement is very good surface finish, close dimensional tolerance, then definitely I will go for a investment casting. But cost should not be an issue. I should be a crorepati. It should not be an issue. Okay, if cost is not an issue, I'll go for wax or in investment casting. But cost is an issue. I cannot afford. I am a small scale industry person with a limited budget. In that limited budget, if I have to produce the components of a good quality, then obviously I have to cut down on my other criterias. So in that way, I have to choose one or the other. Everything has its own advantages and limitations, and it depends upon our end requirements, based on which we have to suitably select a particular pattern material, and the process involved, whether we are going for a sand casting or a metal mold casting or die casting, whatever it is. So the selection of casting process, the selection of pattern material, everything depends upon the end requirement. We have to compromise on one or the other. Okay. So which is the best material for casting? Mostly we use wooden patterns and the metal patterns. Mostly we use wooden patterns or metal patterns. And in high-end applications like aerospace, turbine blades and all, jet engine turbine blades and all, then we come to investment casting. As we go along in trying to understand different casting processes, sand casting, die casting, shell molding, investment casting, centrifugal casting, we will come across different examples. Then you will be able to understand which casting process, which pattern material has to be chosen for a given product. How large patterns are made and used? Exactly. That is where now we are coming into. How large I can prepare a pattern. So if let us say I ask you to prepare, let us say hollow iron pipe. Okay, that I'll come to it later. I'll ask you to prepare a component which is 10 meters height and 20-meter width. Let us assume. I'm just trying to exaggerate to a certain extent. Let us assume I have to prepare a component which is, let us say, a rectangular block of 10-meter height and 20-meter width. So how do you make such large components? Okay, here comes the types of patterns. So how do we select a pattern? Like pattern material, let us say I have selected wood as my pattern material. I'm ready with the material. Now, what should be the shape of my pattern now? As we have discussed in the last class, the shape of the pattern is a replica of your end product. Let us say my end product is a gear shape. My pattern is in a gear shape. Okay. But that is not only the requirement. There are other things which are to be looked into it. And these are the following things. First and foremost thing, which type of pattern that you have to select depends on the quantity of castings to be produced, whether you are going to produce 100 components or 1000 components, that depends. Second is the size and complexity of the shape, whether the shape is a simple, a square or a rectangle or a circle or a sphere, whatever it is, whether the shape is a simple one or a complicated shape. And then next comes the type of molding method, whether I'm going to use a hand or machine molding, whether I'm going to ram it with a hand or by using a machine. Next, the problems associated with the molding operations, such as withdrawing the pattern and all. Now, how well you are placing your patterns inside the sand mold. Okay, the pattern type, the type of pattern that you are supposed to select also depends upon your placement. That means, if I give you a box and ask you to place one cube, a cuboid, a sphere, different shapes I have given, and I ask you to place inside a box. Now, how well you pack so that the maximum space is being occupied depends. Okay, if you keep let us say, a rectangular block vertically, then the space occupied is less. And if you keep it in a horizontal way, the space occupied is more. So depending upon the type of placement of your pattern into the mold also decides one. It is also one of the factor in preparing which type of pattern I have to select. Other difficulties resulting from poor casting design or pattern design. Okay, that is fine. So these are the different types of patterns. You have you can make a solid pattern, you can make a split pattern, you can make a loose piece pattern, match plate pattern, gated pattern, cope and drag pattern, sweep pattern, skeleton pattern, segmental pattern, and a follow board pattern. So there are different variety of pattern preparations. Okay, let us go one by one. The first and foremost is a solid pattern. Solid pattern, which is commonly known to everybody. Okay, so just a minute. Okay, meanwhile, before I proceed for different types of patterns, do you have any queries? See, one more thing, as I'm able to see hardly 300 students attending. So if this is a case, then we can even go with a Google Meet, okay, where we can have a direct interaction rather than looking into the chat box and all. 300 students means hardly it's a 4 links that we can use. No? Yeah, tell me, if only 300 students are there, then we can go into the Google Meet and directly discuss there itself, where we can have a live one-to-one interaction directly. Yeah, somebody is asking, instead of using metal for making pattern, can we coat wood with some water resistant paint? Then we can overcome the problem of absorbing water and swelling. Yes, yes, you can always do that. But that also, the see, even when you paint it, but still the moisture content will go through the pores of the wooden, which you cannot avoid that easily.